Okay, it's rolling, right?
Yes.
Okay. Are you able to see my desktop?
Yep.
Yes.
Okay. Okay. So good evening, everyone. I'll be giving an overview of OpenMP. So this will mostly be a 10,000-foot overview of what OpenMP is, with some. I'll not dive deep into the code and stuff, but yeah, it will be since it's a huge library and stuff. I'll try to cover as much as I can. Okay. Please feel free to ask me any questions at any point of time. And yeah, so before I begin, I would like to give a little disclaimer that I haven't used this in a professional environment. So I don't use this at work. I have purely pursued it from a hobby perspective. So I apologize if if there are any wrinkles in this PPT. Okay. So what is OpenMP? OpenMP is one of the ways to introduce concurrency in a system. So concurrency means when multiple things are happening at the same time in a system, and parallelism is a way to introduce concurrency in a system. So you can think of parallel computing as a subset of concurrent computing, and OpenMP tries to implement uh, parallel computing by using multi-threading. So usually OpenMP will distribute a task among threads, and it will allocate those threads uh, on different processors based on the decisions made by the OpenMP runtime. And OpenMP libraries can be used with C, C++, and Fortran. Okay, so let's start with a broad overview of why we need to parallelize. In the ye old days of 2005, um, uh, your hardware automatically improved uh, roughly around every 2 years, thanks to something called Moore's law. Moore's law sort of holds true even today as we move to you know we now have uh, uh, VLSI technologies for 5 nanometer, 3 nanometer ICs. So yeah, it kind of still holds true today, but the majority of computer architecture has moved to uh, multi-processor layouts for a majority of consumer electronics. So improvements in software automatically came with improvement in hardware. So software which used to run slow 2 years ago automatically ran faster because it got better hardware uh, with almost twice the uh, twice the improvement in clock speed. So basically, improvements until now, software engineers were accustomed to getting their um, improvements from the underlying hardware, but this no longer holds true because an increase in frequency also demands a higher voltage from the power supply, which introduces the overhead of power dissipation in any electronic circuit. I will attempt to. This is about the only shoddy math in here. So if you see power active power in a given circuit is given by capacitance times the voltage square times the frequency. So if a normal processor consumes P1 power, and instead of this architecture, we introduce another architecture which has two processors running at half the frequency. Okay, so if we introduce more electronic components, might the capacitance might more than double. The voltage required might more than half because of that, and these processors run at half the frequency of the original uh, architecture. But even though this is not perfect, still we managed to get the same performance with uh, around 40% of the power that was used in the original architecture. So I guess this convinces you to, I mean, parallel programming is here and it is here to stay in the long term. So we better get accustomed to it and design our programs accordingly. Okay, so uh, how does OpenMP use parallelization? It provides an API to write multi-threaded applications. So you don't normally need, uh, uh, I mean, you can use any library to write multi-threaded applications. Each language has its own. Also, there are several other libraries like Intel TBB and Intel Silk and many others, which provide threading support. And but OpenMP simplifies uh, a lot of pain is uh, which we see in developing multi-threaded applications. So how OpenMP does parallelization is by using a set of compiler directives, which are pragmas, and some library routines. OpenMP pragmas follow a generic pattern of OpenMP pragma, OpenMP, and the construct name. And different constructs will provide different um, features of the library. And every pragma or every construct applies to a structured block. Okay, so typically you would have a bunch of code below this block, and this pragma or this property would apply only to this code, not not to anything outside that code. Okay. um, Um, so a bit on the pros and cons of multi-threading. With multi-threading, you have faster communication between threads. Each thread has, I mean, there is threads can store data between them, and it is especially beneficial for large data sets where you can distribute your data between different threads and essentially um, uh, wave off your load across the system. And threads are, as I said earlier, they are extensively supported across languages and frameworks. Some problems which we face during multi-threading are you extensively have to take care of data races, and it is multi-threading is difficult and expensive to develop and debug, since you need to use so many synchronization mechanisms. There is a limitation on process memory, so each thread shares data with all other threads in the same process. So if the uh, process runs out of memory, then the threads will run out too. And if a thread crashes, your process will also crash. That this this is also a major drawback, and it is not scalable across machines. Multi-threading essentially is a localized operation. You cannot invoke threads across a different machine without using any message passing interface. Uh, and Yeah, okay. So the first form of parallelization which OpenMP provides is SIMD. SIMD stands for Single Instruction Multiple Data, and these are essentially this is essentially taking advantage of the hardware registers that are available on modern processors. So with along with um, scalar operations, you have scalar registers which store normal values. You have vector registers which can be up to 512 bits long, and these are divided into blocks of say 32 or 64 depending on the architecture. And this is the hardware parallelization at the highest level. So you have one single instruction which takes in a bunch of data, say 8 bytes or 16 bytes, and in one instruction it will process all that data and give you the output. So for example, if you have a small enough vector which can fit in say 512 bytes, you can essentially operate on all data in that vector in one single instruction. And here we are talking about one single assembly instruction, and these assembly instructions are provided as vector extensions to the hardware instruction set. So the Intel x86 hardware instruction set has vector instructions by various names. There is SSC2, there is AVX2. You can actually see which instructions you have by checking cat proc CPU info. So if I check for AVX, okay, so I have AVX and AVX2 as well as SSC2 instruction sets. So different families of instruction set provide different operations. Some are geared towards multimedia operations. For example, the SSC stands for streaming set, uh, SIMD streaming extensions or something like that. So it is geared towards uh, processing streaming data, that is multimedia data in a parallel way in the CPU itself. Okay, so you can have speed up to 16x for single precision floating point operations and up to 8x for double precision floating point operations using SIMD instructions. Um, in most of the cases, your compiler will auto vectorize your code. You don't need any external library to do that. But compilers are pretty conservative in their approach. If they cannot prove that there is data dependency, or the vector is not dependent on any other uh, in itself, or any other data, the compiler will not vectorize your code. So in the first example, your code is dependent on the previous element, this, and this is essentially a non-vectorizable operation. This is a trivially vectorizable operation. The compiler is smart enough to figure out that there is no data dependence in the vector itself. So it will go ahead and vectorize. Um, in some cases, it is not apparent. For example, in this case, if the vector length is greater than is less than 16, This is a non-trivial case, and similarly in this case, if A and B are pointers, so A and B can be aliases of each other, or sizes of both can be different from each other. In both these cases, the compiler will not vectorize your code. Um, so you can so this is the first pragma that I want to discuss, which is pragma IV depth. It is somewhat uh, uh, it's somewhat non-trivial to use this. I haven't seen many cases where this has been used, but it essentially tells the OpenMP. It essentially tells your compiler to drop multi-versioning. So what multi-versioning? In case of in case where it is not trivial, compilers will generate three versions of the same program. First is a scalar version, which is a normal a sequential code. Second is a masked vector version. So uh, it, uh, it is essentially vectorized, but with some bit masks. And third is the fully vectorized version, that is without the bit masks. So um, it essentially promises the compiler that there is no pointer aliasing, or the data is essentially different from each other, and you can go ahead and vectorize the loop as you want. But okay, so the scalar and vector version will introduce some pointer aliasing overhead at runtime, and this pragma IV depth is essential for that overhead to be reduced. This is the first pragma where we can declare our function as SIMD. So this enforces vectorization by generating more than one version of the function for being called in a SIMD loop. So, for example, if you are working on a function which has uh, uh, if you're working on a function which is to be called on a vector, you can declare that function as a SIMD function, and you can automatically get three versions of the uh, function at and the compiler will check at runtime if there is dependence between data provided to the function or not, and depending on if there is dependence, it will call the scalar function. If there is no dependence in the data, it will call the vector function. um, the second pragma OMP SIMD reduction ensures that there is no data race in writing to the shared variable. I think I should. Uh, is it okay if I? Is everybody able to see the screen and the code?
Yes,
Okay, and is the font size okay?
it looks fine.
Okay. Okay, so this is one example that I'll be trying to use in throughout this presentation, and it's a simple numerical integration problem. So if let's say you have to find an integral of a function from a to b, you integration is essentially the area under a curve. So you can what you can do is you can divide the area into little rectangles, and the summation of area of all these rectangles will be equivalent to the uh, integral value. So Okay, so this is my okay, so this is my black box function. This is the function that I have to integrate over ANP, and my worker.cc calls this integral. So what it does is it computes. First, it computes the midpoint of the rectangle. So this is the x coordinate, and this is the uh, value at. This is essentially f of x, and the area will be uh, y into x, which is di, and in the end, I uh, add all these areas to I to get the total area under the curve. Okay, so using this, and just to, I'm calling all this from main. Okay, so I am calling this function 1 billion times, and the performance that I got from this was okay. So let me just show you the compiler flags that I had used. This is just with the fast optimization, which is the fastest, which is the optimization for the fastest runtime. Okay, and uh, so this takes around 10,000 milliseconds, which is 10 seconds, and the yeah. So in total, it takes 10 seconds, and it's not a lot of time, but we'll see how we can reduce this with OpenMP. Okay, so I have described these two pragmas. Let's see how we can use these in. Okay, so this, first of all, I declared my function in library.cc as SIMD. So OpenMP can now take my function and use it in parallel with uh, in this loop. So why did I have to use SIMD reduction? Because the value of di was being written to I. So I is sort of a shared variable between all the instances that will be spawned when this will be parallelized. So there is a possibility that a data race will occur on I, and the results will not be correct. So a SIMD reduction, so reduction is a common parallel programming technique wherein you, let's say you have 1, 3, 5, and 7. So you will compute the sum of 1 and 3 as 4, and 5 and 7 as 12, and then ultimately reduce it to 16. So this is something that reduction does. It will, so uh, a local copy of DI is made for all um, cache cache lanes. I mean, technically, we are not using threads here. We are just using we have marked this function as SIMD, and we are using the compiler internal vector intrinsics for this. So you can use compiler intrinsics without OpenMP for this, but you have to you sort of have to dig in and find out what your compiler extensions are and which ones are supported, and OpenMP takes care of all that jazz. Okay, and this pragma basically says that you have to reduce on this plus operation, and for this variable I, and this pragma will only apply to the block below pragma. It won't apply. So a pragma in OpenMP means there is one entry point and one exit point. There can't be it can't be called from anyone else, and there is no sharing of any kind. So if we using these constructs, we have a pretty good performance bonus of it's almost a 10x performance boost. The previous time uh, without any pragmas was 10 seconds. With by using pragma OMP SIMD and SIMD reduction, we are we have reduced the runtime to 1 second, and the accuracy is pretty good as well. It is this figures are pretty close to zero, so that's a good thing. Coming to how OpenMP uses threads, this is the main parallelization construct used by OpenMP to parallelize your data across uh, threads. This Pragma OMP parallel will spawn a number of threads, and the data outside this block is shared by threads, and the data inside the Pragma OMP parallel is sort of local to the thread, and that locality and this data is maintained in the thread local storage. So it's parallel, it's private to the thread. OpenMP also provides some constructs to manage data access. So if you want to declare new shared variables which will be shared across the threads, you can use this Pragma OMP parallel shared construct, and there is a private construct to which will make that variable private to each thread. Um, Pragma OMP parallel can also be combined with another construct called Pragma OMP for. So together they become Pragma OMP parallel for. And what this will do is it will spawn a bunch of threads and uh, uh, parallelize it over a for loop, which will and the data in for loop will be spread across each thread. So how, okay, so this is a simple example of what happens, of what will happen if you call Pragma OMP parallel num threads. So you can set the number of threads via an environment variable, or you can use a construct like this to set the number of threads. Um, let's say you have a piece of code and you call a foobar with uh, 4 threads. So internally, it will produce a wrapper function, a thunk, and this thunk will call this will be generated by the compiler itself, and yeah. So once the function is generated, it will call the underlying thread creation API. So for uh, Linux, it will be POSIX threads. For Windows, it will be Windows's native thread library. And so one thing to note here is that it will call for the threads which are non-zero with thread ID with non-zero, because thread ID 0 stands for the main thread itself. So every time you fork of a main thread to produce child threads, you will have a main thread with thread ID 0, and the child threads then we'll have thread ID 1, 2, 3, 4, and so on, based on the number of childs you create. Once you run this thunk function with all these threads and the thunk function separately for thread ID 0, um, you can, I'm sorry, that's a little hidden. So you can join these threads and uh, uh, so this is sort of the thing that uh, this little statement will do for you underneath the hood. And okay, and this is a massive oversimplification, but yeah, the main process goes something like this. You can also schedule threads, and you can, so OpenMP provides different mechanisms on depending on how you want to schedule threads. So you can schedule threads in a round robin way. For example, uh, uh, for example, data at index 0 goes to thread 0, data at index 1 goes to thread 1, data at index 2 to 2, 3 to 3, and so on. And data at index 4 will go back to thread 0 if you have number of threads as 4. Um, so the thing I just described uh, is the static scheduling mode. There is also dynamic and guided scheduling mode. Static is round robin. Dynamic is sort of first come first serve basis for scheduling threads. So, for example, data at IDs 1, 2, 3, 4 will be passed on to one thread, and so on. And uh, once each thread is done, whatever thread comes first, next chunk of data will be served to that thread. The third is a guided mode. Guided mode is a little smarter. It it basically watches which threads, which computations are taking a long time, and then balances the workload accordingly. So okay, so in static, the allocation is pretty dumb. Dynamic and uh, in guided, if a single thread is taking a long time to complete, there will be it will be assigned less data on completion as compared to its current run. So you can, and there is also auto, which is not mentioned here. And auto guided mode is basically up to the OpenMP runtime. Whichever there is a set of parameters that it looks at, and it decides the thread scheduling at runtime. So once we are using threads, a construct called synchronization becomes important, so that we don't have data races which could seriously impact our operation. So OpenMP provides three high-level constructs for to prevent data races: critical, barrier, and atomic. Barrier is pretty simple. All threads complete their computations and wait at a point for each other to complete. And once they are done, they will the execution will continue further. Mutex, or mutual exclusion, defines a piece of code which can be accessed by a single thread at a particular time. And once that thread is done, another thread will take up the execution of that critical section. And atomic is a specialized form of critical section, where which is sort of available for some simple operations, but uh, it has less overhead than the critical section synchronization mechanism. Okay, so for example, the Pragma OMP parallel construct. This will spawn a number of threads, and each thread will get its thread ID. It will do some calculation, and at this barrier, it will end before proceeding further. Because you see this array A is used in some other calculation P. So we need to ensure that the computation of A is correct so that we have our B correct. Okay, so this is the barrier uh, synchronization. Critical section, this is critical and by far the most used. Critical section this pragma defines a critical section, and this will be accessed by a single thread at any given time. So even though all these operations are can be done parallelly, as soon as a thread enters a critical section, it uh, only one thread is allowed to change the value of this variable at a time. And there is an atomic synchronization mechanism. Atomics uh, are a single operation which can be only applied to scalar quantities. In the previous synchronizations, these could be applied to vector quantities as well, but atomics are only applied to scalar quantities, and there is a very limited number of uh, operations which can be used in atomic. So once again we define all these threads, and both of these operations continue in parallel, and once they are done, only the value of x is updated atomically. That is, and this is ensured by the operating system. Uh, this is something that OpenMP does not have to worry about. So hence there are only some operations which can be used in this pragma. Okay, so let's move on to our case study. Uh, we have seen an improvement of 10x once we used the Pragma OMP SIMD and SIMD reduction. And let me show you the code for Pragma OMP parallel. Pragma OMP parallel will implement multi-threading, and we will use reduction with Pragma OMP with the reduction mechanism. So okay, so we have covered SIMD. Let's go to by the way, you can get the vectorization info in GCC by this option, fopt info all, and you can specify a file name to get uh, to print this optimization info. Um, okay, so in the header file and the implementation file, we declared our functions to be pragma to be SIMD, and along with now what we did in this loop was pragma OMP parallel, which spawned multiple threads uh, to to parallelize the for loop, and along with that we used SIMD reduction on variable I. Combine yeah, all that our main.cc remains same throughout. So combined with all these pragmas, our our execution time came down to 0.3 3 seconds. So that is 300 milliseconds. This is quite an improvement from the 10,000 millisecond execution time that we had. And I have one final example for this, which is um, again, I have declared my function as SIMD. In this one, I will combine all the constructs that I have used. So this will contain pragma OMP parallel, pragma OMP 4, and this critical section for computing. Okay, so all these threads, since the second thread, the innermost loop has a dependency on the outermost loop, we had to hint our compiler to force vectorization on the outermost loop. Okay, and since this is dependent on the individual values of di, which each thread will calculate, we have defined a critical section where only one thread is allowed access at a given time, and the yeah. So for this is the critical section, and this will only be accessed by a single thread at a given time. So that is the concept of mutual exclusion. So each thread will wait for each other to complete the critical section. And sorry, this should be, okay. So yeah, there is not much performance improvement in this. So this is very situational. You can get performance improvements in using some constructs, and you may not. But yeah, these are pretty similar, and per you can use OpenMP to your advantage by since all major compilers ship with OpenMP. There is Intel Visual Studio supports an older version of OpenMP. GCC supports, and Clang supports as well. So you please go ahead and make your code super fast. Yeah, that's about it. Hello,
Thanks, Chaku sir.
Eric. You can stop the recording now.
Yeah. Wait a second. Acha, so like where is OpenMP actually used? Like
Where is OpenMP?
used like regularly? Like where do you see OpenMP working?
Mostly, so what I did was I ran LD user bin for everything in user bin, I ran LDD. So a bunch of multimedia applications like my audio player,
Mm-hmm.
Amarok. I saw the lib OpenMP was linked to the executable.
Mm-hmm.
In Tesseract, I saw OpenMP being used.
Mm-hmm. Makes sense.
I guess VLC. So mostly computationally intensive applications might use OpenMP.
So what does so do frameworks like TensorFlow and other machine learning frameworks also use it for parallelization? Like I
Yes,
think they do
yes.
use SIMD, right?
Yeah. Of course, they have to use SIMD for performance speed ups.
So like OpenMP is a good option for them.
Yes.
And so what is the difference between OpenCL and OpenMP?
I am not sure. I'm not sure,
Okay.
man. I guess, I mean, both, there must be some common area, common ground in between them, but I'm really not sure. Have to look more into that.
So then just does OpenMP work with ARM? Like because it can
Yes,
parallel, it can has ARM, but does ARM have a SIMD extensions?
yes, they have.
Okay.
I saw it somewhere. I think I can find it for you. Yeah, ARM does have support for OpenMP.
Oh, cool.
So SIMD extensions are just a part of OpenMP. I mean, it can parallelize inside the processor, so to speak, so to say, and outside the processor as well using threads. So even if I guess if an architecture does not have support for vector extensions and it supports threads, I guess OpenMP should be able to work with that.
And you also mentioned the atomic part. Like, could you have talk a bit about that? Like how the atomic functions could be working and how are you doing atomic computation? Like, let's compare it with the atomic functions we have in sync/atomic in Golang. They have you can add you
Okay.
unsigned integers and other stuff similar to what is possible here.
I guess on a very basic level, atomics mean which can be computed in a single cycle or something like that.
No. I don't think like atomics mean that it will be updated in this not necessarily a single cycle, but it won't. It will be affected in the single instruction
Right,
because
right.
yep.
Yeah. Okay. Yeah, sorry. So there is a very primitive set of operations which are atomic. So in the presentation, I had some examples. So increment, pre and post increments, and assignment. That is all that you can have in your atomic section.
So you also mentioned one specific case that I minus one wasn't parallelizable because it needed it had a dependency on a previous value. So
Yes.
how does OpenMP work with that? Like that specific
Mm,
case.
OpenMP is not won't be helping you in
Okay.
that case.
Mm-hmm.
So that is something you need to.
Okay.
Uh,
And there was this specific section where you declared shared and private variables. Like, couldn't that solve that part? Why did you require adding synchronization methods like critical sections and barriers and mutual exclusion?
mhm.
When you have something like that shared, doesn't that mean that it will automatically create those synchronization variables for those specific variables? Synchronization sections.
So the thing is, whatever you have inside the pragma scope, that is private to each thread.
Yep,
So
true. So you declared those shared function type in the
yeah,
pragma.
yeah.
What
So
does that mean?
we are specifically marking these variables as shared in order to be so that threads can understand that okay, you can use them to communicate with each other, and uh, that will not cause a data race condition.
No, but like if if they are shared among threads, then they are the cause of the data races, right? That is the point. They should be protected, right?
Not necessarily. If you are reading from these three variables, you can't have a data race, right?
No, because like data races occur because variables are shared across threads. So the point of
A
writing
data
shared
race
should be.
is okay. So there is one additional clause uh, to a situation having a data race, that at least one operation should be a write operation.
Mhm.
You can't have data races. You can't call it a data race if three threads are reading from a single location. At
Okay.
least one thread should be in the write mode for that variable,
Mhm. Okay.
because
So
if
my concept was around that if they are shared variables, they should be protected by synchronization variables. I guess OpenMP works a little differently, where if they are shared variables, um, it means that they're shared among the threads, and thus
yes,
OpenMP can use them. Okay, that's the concept.
yeah, yeah.
Hi, I have a question.
Yeah, go ahead.
Let's say for this OpenMP, the way we can use it for large amount of basically vectorizable instructions. So, wouldn't this be beneficial if you're copying a large file? Let's say, I mean, we are writing big chunks of paged memory. So, can we use this in a vector? I mean, instead of I'm talking with respect to the example you showed, like it was just manipulating integers. But
Yeah.
let's say we want to parallelize, like each instruction itself is manipulating a large chunk of data. Can those be also handled by this pragma? I mean, let's say uh, what I'm trying to talk about is I have a pthread function which copies simply does copy of a block of memory using MCP, right? MCP, right? So can I do the same thing with this OpenCV pragmas?
I guess not. You can use those pragmas to parallelize, but inside those pragmas, you will have to write your own stuff.
Yeah. I mean, I'm not going to call memcp. I'm trying to, let's say I want to devise another implementation of memcp, right? So there,
Yeah, you can.
basically, yeah, okay.
It will just spawn off threads. Each thread will do its own work, provided you
Right.
and provided you handle the synchronization stuff well. You can have
Yes.
an parallel. You can have a parallel implementation of your own function.
Right. Yeah. And just one and a very small question. So, in the compiler generated code that you talked about, we see that threads one to the I mean, let's say we have four threads. We have mentioned four threads in the pragma. Then it would spawn five threads effectively, because the code should. Is that the case? Am I correct or am I wrong there? Just that I want to understand that
So
part.
I mean, that was something which that was an illustrative example to show what a pragma
Okay.
does. So okay, so in the code itself, it will go from 1 till n minus 1. That
Okay. Okay. So yeah, my point was, if I want the pragma to have the 4 tasks done parallelly, it will set it would spawn 4 threads, including the current thread where the code prior to the pragma was executed. That's my point.
sorry, could you please repeat? I
Yeah.
didn't get your question.
So let's say the point at which you insert the pragma into your code, right? Prior to that, whatever code was being executed, we can have, I mean, that code is there, but it would be run on a single thread, let's say.
Correct. Yeah,
And
correct.
when I call, yeah. So, and this is the parent thread.
Correct.
Right. Yeah. And when I call this function, it would spawn another n-1 threads, but the parent